Yeah, so I can't see anything on the screen. You will let me know when I can start?
Yeah, I'll let you know.
Okay. Okay.
All right. So, hi everyone. I think we are live now. Hello all. I'm pleased to have Dr. Tao Zhang with us. He'll be talking about edge computing and fog computing and how it applies to automotive security. So Dr. Zhang is an IEEE Fellow. He's done a lot of research in networks and vehicular security at various executive positions as chief scientist and CTO. He was a chief scientist at Cisco, and now he's at NIST, leading emerging technologies and network services. So, for his keynote, he'll go over how edge and fog computing can be applied to automotive security, and then after the keynote, we'll have questions, some moderated questions, and we'll have audience questions as well. So, without further ado, I'll pass it over to Dr. Zhang and to take over the presentation. Over to you, Dr. Zhang.
Thank you so much. Hello, everyone. This is really a great pleasure for me to be here today and to talk about this very exciting area, edge computing and automotive security. So I will, first of all, start with edge computing and where things are going now. I'll try to take a step ahead to see where things are headed and how this is related to automotive security and what are some of the interesting core issues. So first, where we have come from. Ever since we started centralized computing years and years ago, people in the same time was very actively trying to move data and computing to the edge. So the pendulum has been swinging actually all along. And for example, in the 1990s, the first wave of that so-called edge computing effort resulted in data being moved to the edge, not computing yet. Computing at that time was still centralized mostly. And one of the representative results is the content distribution networks that are very widely used over the internet right now. And then comes the move of computing to the edge. So by the early 2000s, people realized a lot of applications are very sensitive to delay, and network capacity is very scarce and costly. So people are trying to move computing to the edge, and lots of work are being done. For example, a lot of work has been done to consider how do you move computing to the edge in enterprise networks. And other people are thinking about how do you do that in wired telecom networks. And other people are thinking, how do you do that for mobile networks? So one of the representative results out of that effort is the mobile edge computing, or later known as multi-access edge computing. But things started to really taking shape and become faster in development around 2015 timeframe, and when fog computing was launched. So at that time, what we realized was that this disjoint effort actually missed a very important point of edge computing. So that was actually a reason that was preventing the wide adoption of edge computing. So several of us co-founded the OpenFog Consortium together with a set of major players in this area, and to actually spearhead the fog computing concept. So fog computing you can be viewed as an advanced version of edge computing. Specifically, it calls for a seamless computing continuum, all the way spanning from the cloud to the thing. So rather than isolated edge systems and applications as people have been considering previously, and fog computing actually calls for a seamless continuum. So meaning that you can do computing anywhere and depends on your need. For example, depends on your need for performance, your need for privacy, and how much the client wants to be involved in their computing tasks. And also this will allow you to seamlessly integrate the services from edge computing with services from cloud computing, and will make also the edge systems much more manageable. And another concept is that this should be an horizontal architecture for distributing and managing and securing the resources that you're going to distribute to the edge systems, and as opposed to, for example, and developing and separate architecture for different types of industries, different types of application domains, or even different types of networks, as people have been doing. So this concept, if you look at the current popular products, you will see this concept sort of behind many of them now. So now the natural question is, what's going on now and what's going to happen next? And so I think what's going on now is that if you look at especially the research community and some of the leading players in the edge and cloud computing industry players, I mean, you're going to notice that edge artificial intelligence or edge AI is what's happening next. So very naturally, now that people build a continuum of computing platforms and capabilities, and what's come next would be we're going to move AI capabilities to the edge. And so that will include not only just having the edge nodes use AI to do smarter things, but also having the edge nodes do learning locally to help build the AI models that the system are going to use. And so that, I think, is going to go through similar two steps. First, the AI will be moved to the edge. And secondly, and cloud to thing continuum of AI is going to happen very naturally. Actually, that's already happening now in the form of, for example, network AI and network learning. And so then this is just a summary. When we see edge AI takes different shapes. In the very basic form is, let me stop. Looks like this is. At a very basic form is that edge nodes are going to use AI models built by somebody else, for example, by the cloud, and given to the edge nodes. And so here by edge nodes, and I mean those edge nodes can include the systems at the edge of the network, like edge servers, systems, and controllers, and edge routers, and also customer devices like mobile phones, like vehicles, and so on. But more importantly, going into the future is what I call edge learning, which means that those nodes are going to participate in the learning process to help you build the AI and machine learning models that you're going to use. So this has two levels. One of them is this node will be learning under the control of an central authority like the cloud and the cloud system. And then to the future, some of those nodes will be able to learn by themselves without central control, but maybe collaborating with each other. So those edge learning and actually have some unique challenges that needs to be addressed. And people are very, very actively addressing those challenges. We're doing some work here at NIST also. So those, I'm not going to go into the details, just to illustrate. Not only those edge nodes may not, each individual ones may not have enough resources or data to learn well on their own. The data distributions may not follow the common assumptions behind most of the learning algorithms that we use today. So you're going to have to figure out ways to solve those problems. And also, for example, you can't be sharing a lot of data. And so the question then becomes, and why is this important? It's actually not only important, it's necessary for the future. And because a massive amount of data is being created at the edge, and that amount of data is growing very fast. You can see all sorts of predictions, estimates of how much percentage of data is now going to be created at the edge as opposed to in the core. And that calls for learning where the data is. You can't be sending all of those data to the cloud anymore. There's just too much of them. And in many cases, for example, especially in the vehicle case, and what you need to know and is going to change, and you can't foresee all of them. So that calls for continuous learning or online learning in the learning field. That calls for you to continuously to learn. So that is not the way we learn today. Today we train machine learning models by collecting a whole lot of data, sending them to the cloud, and build a model and then send them back for use. And then sort of periodically we send out scout cars and to collect data again. And that's very costly and not timely. So because of this, edge learning is actually becoming so fundamental, not only for creating future AI and machine learning models in general, but also in supporting intelligent networks that's going to rely on those intelligence, like 6G and many 5G applications, like intelligent systems such as automated vehicles. I'll use an example to show some of those. Now let's look at the security challenges, and then we can connect the dots. So if you look at the security challenges in connected and automated vehicles, and you look at how we're doing things in terms of security today by securing other things, and then you think, how do I when I apply this to cars, connected and automated cars, what would happen? So for example, today we secure our systems by first of all trying to fence off threats and with firewalls and so on. And if you apply that to cars, you find it's very impractical to firewall every single car or even every single ECUs on the car. So what does that mean? That means you need abilities to timely detect those compromises, and very often you may have to live with them at least temporarily. For example, you find a virus on a car going 60 miles per hour on the highway, and what do? You need to be able to keep that car safe for at least temporarily before you can take care of that and that malware. And the challenge there is that how do you balance the risk of the malware, the damages that malware might be doing to that running car versus what you can do to that running car to take care of that malware? And so how do we respond to compromises? Today, we are actually very rudimentary in our response to compromises. Typically, we rely on a sequence of shutting things down and checking things up and clearing things up and restarting them. As you can see, this clearly does not work very well for things like cars or other sort of critical machinery and IoT systems. Is unsafe, for example, when the cars are traveling. What do you need? You need risk proportional and fail-safe incident response method. And then we try to detect attacks. We try to detect compromises. And if you think, how do you detect sort of compromises on a car, on a large number of them? So the method that we use today have either problems with scalability or problems with trustworthiness. The scalable ways, for example, and to collect data from the cars, to collect all, for example, selected CAN bus data on the cars. Yes, it can be scalable. It depends on how much you collect. But a sophisticated attack could alter those messages so that it may not be trustworthy, making them trustworthy, and the method may make them unscalable. And so that calls for a scalable and trustworthy detection method. and then you want to contain the compromises you find. And so we have, for example, cars has not only a large number of them, but they use spare parts. And today, for example, we configure the same type of spare parts with the same typically and fixed security credentials, keys on them, just so that and the spare parts can go on any random car later and be expected to work interoperably with whatever is already on that car. And as you can see, that has a problem. I can study the ECU in my lab for a few months and or even longer time, but as soon as I compromise one, I compromised all of the same type of ECUs, and so that can be problematic. So you could need new ways for credential management. And so I'm not going to go through all of them in detail, but this is important. You have to keep the security system up to date. But the cars, first of all, have limited processing resources, and secondly, long life cycles. Over these long life cycles, it's very hard to change its hardware. So the hardware from sometimes is going to run out of capabilities. And so you're going to have to update software and hardware, or you can have you can have off-board security services to complement the aging or out-of-date hardware. And and also you have all of the security operations, and many of those cars are not going to be managed by IT experts like our work laptops. And sending them to those experts can cause intolerable disruptions. So that means we need remote and online threat mitigation methods with minimum service disruption. And that we can't even do very well for our enterprise networks. So you can see there are a lot of challenges. And so we haven't even get into AI-related security issues. There are a large number of them, and also vehicle-to-vehicle security issues that may arise when you send messages between those vehicles, for example, to support advanced capabilities like cooperative sensing, cooperative driving, and teleoperation, and so on. And so how can edge computing and edge AI help? And you can see there were a lot of processings to help secure a car require a lot of data processing and also low latency. Those can be supported. Those type of capabilities can be supported by an edge system. For example, helping the car detect threats. A car has limited capabilities to detect threats itself. So you have to be smart about what you want the car to be detected, what detection capabilities you want to put on the car, what detection capabilities you may want to offload to the edge and the cloud systems, for example, and help cars authenticate, providing credentials to the cars, and local help the car processing data, and even become and distributed firewall for traffic coming to the cars. But that's not enough. And what is interesting is this continuum of compute capability that will allow you to have the car, the edge, and the cloud to collaborate with each other in the detection and assessment, because detecting threats and assessing their risks takes a lot of data and a lot of effort, and it often requires data from multiple cars. Today, for example, risk assessment still requires a lot of human input, and so to smartly allocate the responsibilities and functions across the car, the edge, and the cloud system, and have them work together to detect threats. For example, cars should be able to detect very, very imminent threats, and the cloud, for example, can work on a larger time scale, and ones that requires more data, ones requires more processing, and so on. But those systems can also work together to achieve remote response to the security threats and compromises and mitigation. And that will require you to be able to not only detect threats, because the threats evolve. And so you're going to have to be able to analyze and assess the risks and monitoring and containing those risks, and respond accordingly and proportionally to the risks. And this whole system needs to be highly automated. As you can see, that this goes beyond what we have today, for example, for securing other systems. And last but not least, definitely, is that throughout all this process, you want the car to be able to stay safe, even when they are compromised. And so your mitigation methods needs to be graceful, needs to be safe. And that has to do also and with how much intelligence you want to keep on the car, and how much intelligence and you can supplement from off car systems. So and at the same time, you realize that the distributed edge systems and can also create their own and new security challenges. Those edge systems depends on how you deploy them and how you design them. There can be a large number of them, and they have limited computing resources. And so you need to be able to secure them. So it's a sort of a double-edged sword. On one hand, the edge systems will be typically much more powerful than the user devices like the cars, like the phones, and so that the edge system can help better protect those even more vulnerable devices. But on the other hand, the edge systems will be smaller than the cloud, and there will be more of them, will be working in environments that can be less physically safe. And so you're going to have to be able to secure them. And again, I want to emphasize the point that to secure them and to make sure that you can integrate the services from the edge, is very important that the edge is seamlessly integrated with the cloud and into that continuum of computing that I mentioned before. So if you look at the current challenges that people commonly recognized of using the edge system, a lot of them are rooted or can be traced back to the lack of integration between the cloud, the edge, and the cloud. And so then, so at the very end, let me just briefly mention the ongoing and the emerging research. And so the reason I'm doing this is that by looking at so it's very hard to predict the future, right? And even the near future. But one of the things you can do with credibility is that if you look at what's happening in the research activities in the major players, and those those are where many of the new methods and protocols and standards will then follow. So we talked about the importance of creating machine learning and AI models used by those places, and the edge learning in this. So just use an example to show. For example, it's very essential for creating future AV software. Why is that? Let's take a very simple example. How do we train a car to recognize stop signs and or any other things? So stop signs is just an example. And to recognize any other scenarios, any other objects or combinations of them. So today we send out scout cars all over the country, all over the world, and under all sorts of conditions, and to let the car sort of watch things and collect data and send them back to the cloud and build models. We talked about the limitations of this method. And so you have a car in the sunny sort of country road in the southern part of the country. This is the type of stop signs that the car will likely see and mostly see, right? And then you have another car in my part of the country, the northeast, and this is what you're going to see. And the southern cars may not see those, or may not see them very often, as you know. That can screw their data set. And so you need all of them. So you need send cars all over the place to learn everything. And one of the major problems of machine learning when it comes to machine learning used in cars and any other things is the ability for those models to generalize, meaning that you can only train a model as good as what the training data set can represent. So, and you can't, it's very hard for us to even know whether you had enough data and that represents everything you want to learn. So then the better way to do this will be with edge learning. You have the cars sort of learn where what they can see. You don't have to have every cars to go everywhere, and they can go. They can even continue to learn as they are used. So, and then you figure out a machine learning method and to fuse the knowledge learned by different cars. And this fusion of knowledge could be done by a combination of edge computing systems and cloud systems. And so collaborative learning and end-to-end collaborative learning, we know this car has so much data from all sorts of sensors on it. And the question is, first of all, lots of the data, especially after you learned, you build your initial models, lots of those data do not contain any new information that you is worthy of learning anymore. And so sending all of them to the cloud is, first of all, not practical, secondly, not necessary. And so you have to decide and what data should be processed on the car and how much and which data we should be offloading to the edge and the cloud systems. This include, for example, you do not have to offload only raw data. You could be offloading and sending to the cloud and edge systems the knowledge you learned from your local data. And each individual car may learn a biased knowledge because each individual car may see only one part of a big elephant, right? So it's like touching the elephant. But that knowledge, when it comes from multiple cars into the edge and the cloud system, that can be fused and can be processed together to produce your model. And so then the question is, what should be processed at the edge? What processing should be done in the cloud? And this whole process is sometimes called network learning or network AI. And so the central question is, how should those devices, edge and vehicles and cloud, collaboratively train models? So this is also one of the areas that we are conducting research on. And we think this is very efficient, very essential. Not only applies here, but also applies to more general uses of AI and networks like 5G and 6G. So thank you so much. I'll stop here.
Awesome. That was a great presentation, Dr. Zhang. And I also see a lot of questions in the Q&A tab. So I have some of my own questions as well, but I'll perhaps start with the audience questions first.
Yeah, I don't know how do I stop sharing?
I can't see your
Is
screen
this
anymore, so I think we should be good.
okay? So
Yeah.
I stopped sharing you so you can share your screen. Did I
You
stop
can,
sharing already?
yeah, you've stopped sharing already.
Okay.
So we have the first question on stage as well. I'm not sure if you can see it, but it basically is talking about adversarial edge computing, or the use of edge computing basically for attacking AI and for malicious purposes.
Yes, definitely. As I mentioned, that the edge computing systems do bring its own sort of unique security challenges, and that sort of other people can attack those systems. And when it comes to edge learning, and a special challenge that we are addressing is adversarial attack. And so because edge nodes each individual ones do not have enough capabilities to learn. So when it comes to edge learning, most likely you're going to do collaborative learning, things like federated learning, and so meaning that the model that you build is going to be based on contributions from multiple edge nodes. They are even more vulnerable. How do you detect and sort of reduce or remove the adversarial nodes. Nodes can be totally adversarial, nodes can be compromised and so send you wrong information, and that has been something that is being worked on as well.
Sounds good. We have our next question, which I think
Maybe,
seems to be
maybe just a quick thing. So for people who are asking questions, so once your question is posted, if you want to come on stage, so we will send the invite to come on stage. If you want to come on stage, accept it, and you can ask the question yourself. Otherwise, yeah, Abdul, I will read the question. Right.
all right. So I'm moving on to the next one. I think sort of very similar. That how do you deal with the security of AI itself?
Right. So that's one of the. So I talked with one of the. So security is, related to AI takes different forms, and you can group them in different sort of categories as well. One category is the threat that you encounter while you're building your AI and the machine learning models. So the example that I was using in Edge AI, that's one of them. So you want to make sure that the models you build and it's not sort of influenced by adversarials, overly influenced by them. Sometimes it can be, and so you want to be able to understand that. You want to be able to reduce the impact of that. And another big category of threats related to AI is, as we know, especially when it comes to machine learning, and a machine learning model can only handle what the training data set and represents. So when you can have a good guess of the type of training data that is used to build a model, you can then sort of attack the model by trying to alter the distributions of the actual objects and things that the model is going to handle. Stop signs, for example, there was this famous study some years ago, and that showed that sort of a model trained to sort of recognize stop signs can be easily fooled if you just so put some random small tapes on a stop sign to disrupt to alter the distributions and the looks of those stop signs. And people have did other tricks, for example, to show those type of attacks can occur, for example, by trying to alter the looks of the dotted lines on or solid lines on a road, or other sort of things. Essentially, the category of threats is to try to change or perturb the data you actually have to handle. And another area of threats that are less studied, though, is the threats that comes from the interactions of different AI models. So we have been training AI models to do a specific set of things, but we have not been very careful or even systematic in training AI models to collaborate with each other. And so the cars needs to interact and sometimes collaborate with all sorts of other roadway actors, including other cars. And a growing range of AI-related threats are being identified in those areas as well.
So I'm curious, basically, this collaborative learning and federated learning approaches, let's say like within cars, does that end up improving the robustness of the AI model overall?
So it solves several questions. It solves, and the first question is that in the future, that may be the major way you have. You may not be able to build a quality model without doing edge learning, just because most of the data is going to be at the edge. And just because you're going to have to learn continuously. So your learning is a lifelong event. So the car has to continue to learn. You can't be just saying, I build a model, hey, use it for the average 14 years of your lifetime, or 12 years, depends on the car. That wouldn't work. And today, you do that by sending out hundreds of scout cars all over the place to collect data. And that takes forever. And as you know, sort of one of the major problems of testing the car is that, hey, you have to collect like hundreds of millions of roadway data. It takes forever. And so you can't sort of learning and use that type of learning to update the model. It's very costly, it's very time consuming. And but having the cars sort of equipped with your initial system, but learning as they are being used. And first of all, you have more of them. Secondly, they go everywhere, and then build up your model on an incremental basis as you are learning using edge AI and edge learning. That in the future will be, I think, will become an even more practical way of doing things.
And do techniques like GANs like, do they end up improving the robustness of the model overall? Like, I'm curious about the use case that you mentioned where you can hide a stop sign and basically like fool the car. So if you use like learning models like GANs, like does that make a difference?
Absolutely, yeah. Adversarial learning definitely is going to be important. And for example, we are looking into how you apply adversarial learning in edge learning cases. For example, combining them with data fusion, with model fusion, or with federated learning, or with transfer learning. And to ensure that the model you build is actually robust. And yeah, so definitely.
Sounds good. Thanks, Dr. Zhang. And I'll move on to the next question that we have. So, how do you measure the completeness and quality of data training set? So
Right.
essentially, yeah.
Right. So that's, yeah, as I mentioned earlier, that's a big problem today in AI, not only just in this field, in the automotive field, but everywhere, right? That the root cause of there is the inability to generalize an AI model. And so for that, and both for testing and for training purposes, you need to be able to have a data set that contains sort of everything you want to learn. It's impossible today or impractical today and to have some such data set for vehicle. It's just impractical. It's just too many things, and not only too many things, but their combinations and different under different conditions and so on. So that's why another way of approaching it is continuous learning, and you learn to your best to the best you can do, and to bring the quality of learning and the safety as a result to a level that's reasonable, and at least under certain conditions, and then you continuously learn, and as you grow your applications. And if you think about it, that's the natural way we humans learn. And that's the natural way that any successful products, no matter what it is, actually grow. Yeah, when they grow, so people learn from the experience and so on. And so that, I think, is a more a practical way of achieving the problem. As already the research community has very, very actively been trying to increase the generalizability of the machine learning models. They're making progress, but the progress is not as fast. And so the two-pronged approach is one will continue the research on improving the way we learn to make them more generalizable, and in the same time, there is over the past 2-3 years, there is a sort of exponential surge on collaborative and online learning, which means continuous learning.
On that note, as a follow up to that one, people also resort to synthetic data generation approaches. How robust are those approaches basically when it comes to training machine learning models?
I think it's very, very important, and you can generate synthetic data and to complement your real life data collection, and people can envision or imagine many scenarios or predict many scenarios, And so this is very, as we know, almost every single sort of AV maker or any or other AI model developers for other IoT type of systems, they increasingly rely on this type of synthetic data simulated testing. And I think so that definitely helps. And one of the major problems there, I think people are trying to attack is how do you credibly translate or map what you learned and what you tested, and from those environment into reality. And so that will still require you to build that linkage, and that link I think is still weak today.
Mhm, mhm. Yeah, so moving on to the next question, how do you basically ensure a safe execution of safety features in automated vehicles, and how do you basically ensure in future, do you think HSM cores will be ASIL compliant?
Yeah. So, yeah, that's a question we hear so often, so frequently. And as you know, those level four cars, as you're referring here, rely on more machine learning quite a lot. And machine learning designs software not based on functional requirements, right? They based on data samples. They have no concept of functional requirements. And so because of that, and matching the functional requirements or matching their design to functional requirements has been an issue, has been a challenge. Um, so there are work going on. I wouldn't say there are solutions, and so you could define, for example, as you know, SAE has been defining behavioral competencies. And so for each behavior, how well this behavior can be demonstrated to perform and things like that. And so that's one possibility, but as you know, that you can have so many behaviors and or their components, and the way you describe or measure competence can be very, very convoluted. And so I'm not sure that that is actually that practical. It could be maybe a small step. And so one of the things that we looked into some time ago was to establish the inherent relationships between different functions. So you could sort of figure out and understand or test the performance of certain things, behaviors, functions, and of a car, even if your design is not directly based on that performance, that function, right? Your design is based on data you see, but you can still, but the car still performs many functions and very well. So one of the things that I noticed, but there are actually inherent relations behind the different functions and different subsystems or sub-functions. And so capturing those relations could go a long way in helping us understanding sort of not only how close we are to our final functional requirements, but also when you change the designs over time, part of the system, right? How would that change the overall functionality, and that in the future can also help us determine how do we test and validate.
For sure. And moving on to the next question, I think like sort of similar that at this time most HSM stacks or data exchange between host core and HSM core is safety rated at QM. Security and edge computing expands to critical functions in vehicle. Would this create a demand on having safety ratings for HSM offerings?
I have to admit, I personally have not looked deeply into this question.
No worries. We can move on to the next one. So I wanted to, and this question basically is very I was quite interested in this one. So do we like from a security point of view when you're talking about edge computing and I think like more so for fog computing and this whole continuous computing continuum, uh, like some of these edge devices would lack security controls, right? So training AI or running like compute loads and applications on the edge, like does it become a security concern in that case?
Yeah. Yeah. So one of the key reasons for edge learning, for example, is to allow those edge nodes to keep their data locally without sharing them. And the basic conventional form of one type of learning method that you can apply to this environment is federated learning. And the basic federated learning requires zero sharing of the raw data. However, it does require those nodes to share what they learned. For example, their initial data model. They learned a model, so they're going to share the model. So, in other words, so they share the model then iteratively, and they increase the performance of the model throughout the federated learning process. And so that basically means that what you do is that rather than sharing raw data, you share some sort of knowledge you learned, for example, in the form of a machine learning model and with others. That can help you protect your privacy as opposed to, for example, giving access to your raw data to other people. And there are some smart researchers that who have found, and I can also do something to breach your privacy through the models you send me. And that depends on but that's proven to be a lot more difficult than if I have access to your raw data. And so another aspect of it is that uh, you can also share raw data in this environment, but you can share raw data strategically. You share, first of all, very tiny portion of it. And secondly, you can share them in a way that you have control over. And thirdly, sort of the sharing in that particular case, for example, could be only with core networks as opposed to with each other. So there are sort of different ways to reduce the privacy risks and also other security risks. And as you know, those local data, indeed, because they are on those smaller and less powerful devices, they operate everywhere. They do indeed have an potentially and a larger sort of chance of being breached, right? Being compromised. As they are compromised, and the compromiser and those compromised devices could be used to send you false information to try to distort sort of your learning and also try to and do other things to you.
Sure. And I'm also curious, like in this whole fog computing setup, like is there also a thing where like these devices would be in a more grid-like setting, and they would say that, hey, like I actually have like some idle compute cycles, and you can send me your workload over. Like, is that sort of setup being explored as well when you say fog computing?
Absolutely. And so you can do that in different time scales. You can do that, for example, in fog computing. One of the benefit of the seamless continuum of computing between the cloud and the edge is the ability for the operator and provider of that service to smartly reallocate over time the computing capability. You can send, for example, your servlets and to different places. You can reorganize them, you can redistribute them, you can reinforce them, you can sort of terminate some of them, depends on your need. And you can also do what people call serverless computing, when the customer doesn't care where the computing happens, as long as it meets their requirements. For example, you have products along those lines already. And so that allows you to sort of distribute and manage your resources much more intelligently and as composed compared to, for example, isolated edge systems, and that's been happening. There's another category of things that is you can offload your computing to other more powerful parts of the system, like an edge system or like a cloud system, and on a more real-time basis, on a more sort of shorter time scale. And so those have been very actively addressed in, for example, what people call multi-tier AI or network AI currently.
I think we'll just perhaps like wrap up with one last question. But it's almost time. So this question basically is asking about the demand on EV batteries because of edge computing, because there could be some power hungry compute involved. So any comment on that?
Yes. The resources on a car is definitely and a scarce resources that needs to be very, very carefully used. And so that requires a very careful design of what sort of processing you do and what level of learning and you do on that car, and how frequently they need to exchange the knowledge they learned with other systems. That so the way to reduce the processing and on a car and to reduce the communication overhead so through that learning process is one of the major things that that people are looking into. So that combination, so that calls for remember that collaborative effort between the car and the edge and the cloud, so that you can actually smartly determine and the workload in each different places.
Thanks a lot, Dr. Zhang. This was a great session, and thanks a lot for all the questions to the audience as well. With this, we'll end the session.
Maybe just so,
Thank
Dr.
you.
Zhang, will you be available in the networking session, networking lounge also after this, so that people whose questions we could not get to can ask you there?
Sure, but how do I do that? Can you just bring me there, or do I have to click on something?
We can. So if you go to the lounge, there's a dedicated table for this track.
Okay, I
You can
will
just
do that.
go there. So if you, once we end the session, you'll see the lounge, and then you can add
Okay.
yourself to the table. And
Okay.
to the audience also who want to interact more with Dr. Zhang, please go to the lounge, and you can have one-on-one conversation with him there.
Okay. Thank you, everyone. This is very a good conversation. I really enjoyed it.
Thanks all, and thanks a lot. Take care. Thanks, Dr.
Thank
Zhang.
you.